All right, so let's talk about PA3. If there's questions on PA3. Yeah.
Can you explain hash load?
Hash load?
Or hash find?
Hash find. So hash find is supposed to look for a license plate in the hash table. And you have a function called list find, which takes a list, a license plate, which is the thing you're looking for, and pointers to a first name string and a last name string, right? And last find should search list for that plate, and if it finds it, load data into these two variables, right? That's list find.
It's working, kind of, but when I pass that back to hash find, the strings get lost. Throughout themselves.
Interesting. So in hash find, first and last, right? These are still character pointers, right, which were passed by your main program. So in your main program, you call it like this, right? In your main program, you have to set up space for plate first and last, okay? And those, I said, you can declare statically, so you can make those arrays of 40 or 50 characters each. That should give you enough space, and if you pass just plate first and last to hash find, it should pass those to list find. List find should go down when it finds the sentinel node, the node that you're looking for. Use a string copy, okay? Don't use equal. Use string copy from like node arrow first into first, node arrow last into last.
So can you do a character pointer and then malloc inside of list find?
You can, but I don't know if that would do you any good.
That's what I have set up right now. And it's not.
And then you're copying into that string that you malloced?
Yeah.
Okay, is there a way that you're passing that back to hash find?
I was thinking in main I have the R pointer set up. And then I pass that to hash find, which passes that to list find.
Okay, good so far.
List find mallocs it, string copies in. And then when I print after calling list find in hash find, it's not right.
Right, so inside list find, first is a local variable, okay? You're setting the value of that local variable to an address in memory, and then you're copying into that address in memory. When you come back, the value of first here is the same as it was before you called, right? We pass by value, so this is still pointing to the thing that you sent from main, not the thing that you malloced and copied into, right? That's the problem with pass by value. If you don't do this, then in your main program, you know, you have something like car first bracket 50, okay? So in your main program, when you call hash find first is the address of this block, that gets passed to list find first is the address of this block. When you say string copy first comma node arrow first, it copies into that address, which is this thing right here. So then all the way back up, that's still preserved. So yeah, exactly the right idea, just foiled because it's passed by value. Cool, other questions? All right, well, let's continue with trees then. Yeah, question.
Yeah, so when you dump, it's always going to just, is it doing the same type of printing as if you were to just enter in a plate?
No.
Okay, so it's printing like
Yeah.
date, name, name.
See what the assignment says.
Yeah, okay.
Right, so one of them is last name, comma, first, and the other one is separate lines.
Oh. Play with separate lines, isn't it?
Yeah, or use the sample code, which I can't get to because I don't have a. I don't remember any of my BHG 709. Yeah, you're probably right. Right, so license plate is license, first name followed by last name. Dump is like that.
Oh.
And then load is like that. Unless you do the bar graph, which somebody did, which was cool. All right, so trees. So why do we care about trees? I've told you that trees are good for storing information, but there's other things that we will end up using trees for. For one thing, is when we talked about stacks, we talked about, doing something and going off and doing something else. So, I mean, we can describe that changing tracks and going off and doing something else. We can describe that with a tree in some sense. I start off by doing my homework, and while I'm doing that, I need to go off and answer phone, and while I'm talking on the phone, we discuss food, and so we drive to get food, and while we're doing that, we get gas, and after getting gas, we return to driving, and we stop to get money, and then we return to driving, and we eat lunch. And then we're done driving, and we're still talking on the phone, right? And I hang up the phone, and I go to do some homework, and now I have to feed the dog, and so on. So we can use a tree to keep track of what we're trying to remember to do while we go off and do other things. And it's not a binary tree here, but I could have all these other things that I do where I keep getting interrupted while I'm on my drive to McDonald's, right? And then when I'm done driving to McDonald's, right, I pop back up one level and do some other things. When we start working more with recursion, right, which involves stacks, we'll actually be using trees to represent what we're doing recursively. The fact that we're doing one thing and then we pause that and go off and do something else. And maybe we pause that and do 3 other things and then come back and so on. So trees will be closely related to stacks, which are closely related to recursion. Let me show you something very different we can do with trees. Arithmetic expressions. So suppose we want to evaluate 2 plus 3 times 4 plus 5, and we want all of that minus 6. Okay, I can represent 2 plus 3 with a little tiny tree like this. There's a 2, there's a 3, and there's the operation I want to do on them. And this tree represents the result of doing 2 plus 3, that's the number 5. This tree represents doing the operation 4 plus 5. If I want to multiply those 2 results, I can do this. And this tree says I want to multiply 2 things. What do I want to multiply? whatever is in this left subtree with whatever is in this right subtree. This could be a number, or it could be a whole tree that defines another expression. And this whole thing represents 2 plus 3 times 4 plus 5. And I could say, I want to subtract 6 from that. And now here's a tree that corresponds to this expression. And so when we write compilers that need to take things like this expression on the top and turn it into code that actually performs these calculations, one tool that we use is a binary tree. And we take our expression and we turn it into a tree like this. And we'll see in a little bit that once we have a tree in this form, it's very easy to evaluate the expression. So there's more that we'll do with trees than just store stuff in and pull stuff out. But that's kind of what we'll concentrate on to learn more about trees, and that's what your next assignment will basically be. It's going to be the same database of license plates, but you're going to read in that database file and build a tree out of it. And then use that tree to search for things, and also let the user do some maintenance, like delete things from the tree, and do some analysis on the tree. This is assuming I get the assignment written up today. All right, so let's think about the height of a tree again. We talked yesterday about tree depth, so and I'm just going to draw sort of a generic looking tree. I'm not going to worry about data values. And we talked about the depth of nodes. So here the depth is equal to 0, the depth is 1, depth is 2, 3, 4, and 5. And the depth is the number of hops from the root to the node. So if I want to get to this node that I've labeled depth of 5, it's 5 because if I start at the root, I have to follow 1, 2, 3, 4, 5 hops. Okay. So everybody good on what depth of a node is? Okay, so remember, height of a tree equals maximum depth of any node. In other words, find the depth of each node, and whatever is the deepest, that's the height of the tree. So how do we do that? Well, we're starting from the root. That's the only handle we have to the tree. And we could say, okay, let's move to the left. So our nodes are going to have a pointer to the left called left and a pointer to the right called right. So we can start at the root. And we could say, okay, this node has a depth of 0 because that's the root, always has a depth of 0. Let's move to the left. That node has a depth of 1. Can we move to the left? No. Can we move to the right? No. Okay, we're done. Let's move to the right. This node has a depth of 1. Can we move to the left? Yes. This node has a depth of 2. Can we move to the left? Yes. This node has a depth of 3. Can we move to the left? No. Can we move to the right? No. Well, we got to somehow come back to where we were up here and say, okay, now let's move to the right. This node has a depth of 3. Can we move to the left? No. Can we move to the right? Yes. That has a depth of 4. Can we move to the left, right? And so on. And we have to keep our fingers in different pages of the book so that when we're done reading this section, we can go back to where we were a moment ago, right? So as we're coming down here, I need to remember you know, when I'm way down here calculating the depth of this node, I need to have something reminding me that eventually I need to go to the right of this node and start looking at this section of nodes, right? And when I came down here, I needed to know that I needed to come back here and explore all of that, and then I'll need to explore that, and then I'll need to explore that. And when I'm done with all of that, I'm going to have to come back up here and explore anything to the right of that. So there's a lot of housekeeping to keep track of, okay? And we can do this. We can't do it with just a variable that says when you're done, come back to this location, because we might have to remember multiple locations. It turns out we can use a stack to do this. Every time that we're going to goes somewhere, but we need to remember to come back here, we can save that on a stack. Okay? That is a pain to program. Okay? And we're going to do this kind of thing a lot. So we don't really want to deal with that ourselves. But it turns out there's a way we can take advantage of the stack that's built into the system and do something like this very painlessly. Okay, so I want you to forget most of what we just said for now. And let's rethink what the height of a tree is. Well, it's the depth of the deepest node, okay? If I start with a tree, and let me throw a few more nodes over here to make it interesting. If I start with a tree with a root, remember I can think of this as two subtrees. Here's one, and here's another. I got an entire tree to the left of the root, I got another entire tree to the right of the root. Those trees could be null, but in this case they look interesting. Alright, so these are depth 4. Okay. To find the deepest node in the tree, the whole tree that starts from the root, here's a trick. Let's just look at the left subtree. Let's find the deepest node in this tree, just thinking of it as a tree by itself. Okay, the deepest node in this tree is probably this one down here, and it has a depth of 1, 2, 3, 4. If I just look at this tree on the right, alright, forget about all of that stuff. Think of a tree that's rooted right here. What's the depth of the deepest node? Well, it's this one right here, which has a depth of 1, 2, 3, 4, 5, 6. Well, if starting from this node, my deepest node is 6 hops away, how many hops is that from the actual root? It's one more, right? And if I think of this as the root of a tree, and I know how many hops it takes to get to the deepest node, the number of hops to get that node from the original root is just one more. So where is the deepest node of the tree? Well, it's either in this left subtree or it's in this right subtree. And so the height of the original tree is either the depth of the deepest node in this left subtree or the depth of this deepest node in the right subtree. But if I calculate the height of this left subtree, that is the depth of the deepest node in here. If I add 1 to it, it's the depth of this deepest node in the original tree. So try this on for size. So here's a recursive definition of what the height of a tree is. It's one more than whatever is the tallest height of its two subtrees. This just means the tree starting from the left. This means the tree starting from the right. If I calculate the height of this and the height of this, whichever one is bigger, if I add 1 to that, I should get the height of the whole original tree. So if you believe that, and you don't have to believe it yet, but if you believe that, right, this is a one-line description of how to find the height of a tree, provided that we can find the height of the left and right subtrees. Well, how do we do that? We use this exact same function.
And the base case would just be if you hit a leaf node, return -1.
Base case would be if your tree is null, return -1. So this is our mathematical induction cheat, right? I can find the height of trees that are this tall. My friend can find the height of trees that are shorter than that, right? So I'd make this slightly shorter tree, give it to my friend, say, tell me the height. Give them this slightly shorter tree, give it to my friend, say, tell me the height. If they tell me height of 3 and 6, I'll say, okay, the original tree had a height of 7. And I'm guaranteed to be right. How can you prove that? You could use mathematical induction.
So, you're saying that the base case is return -1 if it hits null?
So this approach won't work forever, right? I can't just keep asking other people to find the height of other trees,
Yeah.
because I'm never going to get an answer, right? So we need this to stop at some point. And if someone asks us to find the height of an empty tree, we don't have to use this recursive formula. We can immediately say the height is -1, because we said by convention that's what the height of a null tree is.
Okay, I think I'm grasping it a little bit better. What threw me off was that eventually all of them are going to return null, right? Because it gets to the end.
Yeah.
And so you return null and that one returns where it was left off.
Basically.
Okay.
So this will bake your noodle if you try to actually understand it, which is not a bad thing. So here's my root. Let's say I want to find the height of this. Okay, according to my recursive formula, this is equal to 1 plus the maximum of the height of this, that's the left subtree, and the height of this, which is the right subtree. Okay, how do I calculate the height of this? That's equal to, so let me make a new call frame. So the height of this node, single node tree, is equal to 1 plus the maximum of the height of the left subtree, which is null, and the right subtree, which is also null. Okay, so I call the height function again, and I hit my base case, which says, oh, if the tree you're trying to find the height of is null, just return -1. So this is -1, this is -1, the max of those is -1, 1 plus -1 is just equal to 0. So the height of this single node tree is a 0.
Okay. So
Now
this
it's,
max function,
yeah.
is that something that's baked in, or is that something
Just take two arguments, give back the biggest one. That's a 224 exam question. Yeah. So let's run down the second argument. Let's find the height of this tree. That's 1 plus the maximum of the height of the left subtree and the height of the right subtree. And to find the height of the left subtree, right, we'll go through all of this stuff again. We already know that's going to come back with a 0. So this is going to be a 0 and a 0. The max of those is a 0. 1 plus that is going to be 1. So the height of this tree will be 1. The max of those will be 1. 1 plus that will be a 2. So when I call height on this tree, it should come back with a 2. 1, 2. That's the distance to the deepest node. So what does this look like in code? Root's null, return -1. That's our base case. Otherwise, recursively call the height function on the left and right subtrees. I'm going to save those in integers called left height and right height. And if left height is bigger, I'll just return left height +1. Otherwise, I'll return right height +1. There's not even a loop in there. There's no fors, there's no whiles. There's nowhere that we like have a counter that we keep incrementing every time that we go down further. There's no stack to keep track of where we are. And we can write this in 2 lines of code if we want. We can bundle those calls to height and that if statement into a single. This is a 2-line function. That does a lot, right? But it's recursive. It's cheating because we're using a really powerful function in here called height. Right? It just feels a little weird because that's the function we're writing. That's recursion. So think about that, but not too deeply maybe. Keep it in mind because the definitions we're going to develop and work with for some of these other functions are going to be recursive. Okay? Just because that's sort of the most natural way to do some of these operations, but it's not something to shy from. It's something that's actually going to make our lives easier. So let's talk about printing the contents of a tree. So I'll go back to putting numbers in here. So this is a binary search tree. And when we talk about printing a tree sounds funny. We use a fancy word, traverse, because we're computer scientists. We say we traverse a tree, okay? So traversing a tree means starting from the root, we want to visit every node. Visit just means we want to somehow get to every node. And typically, when we visit a node, we're going to print its data value. So to traverse a tree mostly means we're going to start at the root. We're going to somehow go through the data in that tree so that we encounter each node, and as we encounter it, we're going to print it. And traversing is a general thing for data structures. We can talk about traversing lists, trees, other structures. Yeah.
So when you have the max function that takes in both of those heights, right? Does it call both of those height functions at the same time, or does it do like a one then the other?
So this is pseudocode, right? This was where I broke it up into call the height and save it in that variable, call height on the right and save it in that variable, and then this was my max function. If the left is bigger, I'll return left +1, otherwise I'll return right +1. But this was really just pseudocode for find the largest of these two, add 1.
Right.
return that.
Couldn't you write like a maximum thing though, that takes
Yeah.
in those two?
Absolutely.
And then in that case, what would it do?
In that case, before it calls max, it will call height, come back with an integer, it'll call height again, come back with an integer, and then it will put both of those onto the stack and jump down to max, and it'll pull those values off the stack. Yes, that's what actually goes on. All right, so traversing a tree. The root is always at the top. I'm not going to label it root anymore, but the root is always the thing at the top. There are at least 3 or 4 ways to traverse a tree. But I want to start with one called LNR, which is sometimes also called in-order traversal. So LNR traversal is one way we can start the root and go through and visit all the nodes in a tree. And this is going to be a recursive definition. So LNR traversal. How do we do this? 3 steps. First step, traverse the left subtree of the root. Second step, visit the root, so print out its value. And third step, traverse the right subtree of the root. With a special check in the beginning. If the tree is null, do nothing. If someone asks you to traverse a null tree, you don't have to do anything. There are no nodes to visit. So don't try to traverse the left subtree of the root, because there is no root and you'll segfault. Or just lose your mind or something. But assuming the tree is not null, it has a root, so traverse the left subtree of the root, visit the root, traverse the right subtree of the root. All right, and the sample tree I've drawn is a binary search tree. What makes it a binary search tree? What's the property we need?
Only 2, or at most 2 child nodes per
At most 2 child nodes, that makes it binary.
And then is it that everything on the left is smaller, everything on the right?
Everything on the left is smaller than the node that it's the left of. Everything to the right is bigger than the node that it's the right of. Okay, so let's do an LNR traversal on this tree. Okay, so here's the tree I'm passing to my LNR traversal. First thing it should do is see if the tree is null. It's not. It's got a bunch of nodes. Next thing it should do is traverse whatever is to the left of the root. So we should do an LNR traversal on this tree. Okay, trying to write out recursion on paper is difficult at times. And we normally won't have to do this, but I want to do this for now. So I'm going to write out the steps of this algorithm based on this tree, okay? First thing I'm going to do is traverse this tree. Second thing I'm going to do is visit the root. And then the third thing I'm going to do is traverse the right subtree, which is this. And then my traversal is done. Okay, how do we traverse this tree? First thing, see if the tree is null. It's not. Traverse the left subtree, so we have to do 3 things. First, traverse this tree, which just contains a 5. 2, visit the root, which is a 10. 3, traverse this tree, which is the right subtree, which is just a 15. All right, how do we traverse a tree containing a 5? First, see if the tree is null. It's not. So we have to do 3 things. Traverse the left subtree. Well, this thing has a root and nothing else, so the left subtree is null. And then we have to visit the root, which is a 5. And then we have to traverse the right subtree, which is also null. All right, we're still inside step 1 of our call to traverse, which was to traverse this 3-node tree. And the first step of that process was to traverse this 1-node tree. And that takes the following 3 steps. First, traverse a null tree, then visit a 5, and then traverse a null tree. Okay, so we're going to call traverse on null, and the first thing it's going to do is say if the tree is null, do nothing, just return. So this doesn't do anything. And then we're going to visit the 5. Okay, so I'm going to say when we visit, we're going to print something. So let me make a table down here to show what we output. Okay, when we visit the 5, we're going to output a 5. And then we're going to traverse null, which does nothing. And now we return. We've done the traversal of a 5. Now we visit the root of this tree, which is a 10, so we print out a 10. And then we traverse a 15. Well, how do we do that? First we'll traverse the left child, which is null. Next we'll visit the root, which is 15. And then we'll traverse the right child, which is also null. And traversing null, we'll come back. Visiting the 15, we'll print out a 15. Traversing the null, we'll come back with nothing. And now we finish the traversal of this 1-node tree with a 15. Guess what? We just finished the first step of our first call to traverse. We have traversed that tree. Next step, visit the 20, so that gets printed out. And last step, traverse this tree containing 2 nodes, 5 and 40. So step 1, traverse the left subtree of this, which is null. Step 2, visit a 40. Step 3, traverse the right subtree, which is a 50. All right, traversing null, that comes back right away, doesn't take any action. Visit the 40, that will print out the 40. And now we have to traverse a 50, and we've done this a few times already. We'll traverse the left subtree. We'll visit the root, and we'll traverse the right subtree. Traverse null doesn't do anything. Visit the 50, prints out a 50. Traverse the right subtree doesn't do anything. It comes back. We have finished traversing the 50, which means we have finished traversing that subtree, which means we have finished our original call, which was to traverse this tree. And what did we print? We printed the data in that tree in increasing order. So if you do this LNR in order traversal on a binary search tree, you should end up visiting the nodes in increasing order of their data value. That's why it's called in order. Well, that's one reason. It's really not. So if you build a binary search tree, we can pull our data out in sorted order by doing this LNR traversal. And it's called LNR because the algorithm is first go to the left, that's the L, then visit the root node, that's the N, then go to the right, that's the R. We could write another algorithm called RNL, and step 1 would be traverse the right subtree, then visit the root, and then traverse the left subtree. Guess what happens if you do that? You get your data in decreasing order. And this is a massively recursive definition of how we traverse a tree, because other than, visiting the root, the other steps are traverse a subtree. But anytime I take the left or right subtree of a tree, of a root, that tree is going to be shorter. It's not going to have as many nodes in it, right? Which means that each time I do this, my number of nodes is going to decrease. And whatever number I'm starting at, 1,000,000 nodes, 1,000,000,000 nodes, after enough calls, I'll get down to a tree with no nodes. That'll be null, and when I try to traverse that, I'll come right back out of there. And that's sort of the end of the rabbit hole. That's where you start popping back up out of the recursion. And coding this is 4 lines of code. Right, so we make a function called traverse that takes a struct node star called root. First we say if root is equal to null, return. Then we say traverse root arrow left. Then we say print root arrow data. Then we say traverse root arrow right. That's all you got to write for this function. There's other orders we can do. We can do a node left right, and that looks exactly like this, except step 1, visit the root, step 2, traverse the left, step 3, traverse the right. So node left right. We can also do left right node, step 1, traverse the left, step 2, traverse the right, step 3, visit the root node. And you get different things by doing things in those different orders. But if you want your data in sorted order, left node right. So I don't want to jump into code quite yet. I want to keep thinking about these things more abstractly. And this is all pretty abstract, right? I've used root arrow right. I haven't shown you what a root node structure looks like, but you can probably imagine what it looks like. It's like a list node, but with an extra pointer. But I want to stay at abstract level for the next few minutes and then get into code tomorrow. So suppose we wanted to search a tree for a piece of data. Well, we know how to traverse a tree now, which means that when we visit a node, we could check to see if that's equal to the thing we're searching for. And if it is, we could set a flag or do something so that when we finish traversing the tree, we know if we found our piece of data. That's too much work. So let's think about this differently. Here's a tree, and I want to know if the number 30 is in there. Well, I can traverse through and check every single node and compare it to 30, but there's a recursive way we could do this. Because if there is a 30 in this tree, it's got to be exactly one of 3 places. It could be at the root, which is easy to check. Right, if tree arrow data equals number, we're done. If it's not at the root, it could be in this left subtree, or it could be in the right subtree. If it's not the root and it's not in one of those left subtrees, we know it's not in the tree, right? So what does that look like if we write it up? So let me call this root. So we'll write a function for searching. We'll pass it the root of the tree, and we'll pass it a number we're looking for. If root arrow data equals num, return true. This is pseudocode. If it's not equal to root, we could check the left subtree. So let's search the left subtree for num. If that's true, then we'll return true. If that's not found, let's search the right subtree for num. And if that's true, return true. Otherwise, return false. That's a perfectly fine search function for a binary tree. Does this look implausible to anybody? I mean, searching a tree is a complex operation, and we do exactly one comparison, which is in that first line. We check to see if the root's equal to the number. That's the only place we actually do any work. But this will actually search the entire tree and give you the correct answer. It only works, this only works because these work. And these only work because this line is guaranteed to work if the root of a tree is the number you're looking for.
We would need to check for null in this.
But you need a base case,
Okay, we'll still do that.
right? Because if the number is not in your tree, you're going to keep moving to the left and the right, and eventually you're going to search a null tree for your number. And first thing I'm going to try to do is see if that null has a data value that matches the number. That's a seg fault. So we need a base case. If the root is null, then obviously our number is not in there because there's nothing in that tree, so we can return false. And if it's a binary search tree, we don't actually have to search both the left and right subtree. We can be a little fancier because if we're searching for a 30, we know 30 is bigger than the root. It can't be in the left subtree. If it's a BST, it's got to be in the right subtree. So we only have to search root arrow right. And if that returns true, then true. If it returns false, then false. If we're searching for a 15, that's smaller than 20. We only have to search the left subtree. But if we don't want to think that hard, right, we can just search both subtrees. And if it's not a binary search tree, this will still search every node. Okay, this is classic recursion. And it should look a little spooky. Maybe not all the time, but once in a while it should sort of startle you. Unless you're just naturally really comfortable with this or you've done recursion before. Because it feels like cheating, to me at least. Right? It feels like I'm not actually doing any work. But if you have faith that these are going to do the right thing, then you've got to admit that this is going to do the right thing too. And I have faith that these are going to do the right thing because I believe this is correct, because these are going to do the right thing. Right? It's a recursive proof. That's what mathematical induction is. All right, so we can search for data. We can traverse the tree. We can add things to the tree. We can delete things from the tree. Deleting is fun. We can analyze the tree. We can calculate its height. We can see how balanced it is, see if it's got about the same amount of stuff on both sides. Okay, all of that we'll go through in precise detail, and you'll be doing those things for PA4. So you'll be building a tree that stores license plates and names. It'll be keyed on license plates, so it'll be sorted as a binary search tree based on license plate, and we'll be able to pull out information, add information, and so on.
Will we be using like the hash function again to kind of?
No, there'll be no hash function this time, because it's just going to be one tree.
Will it be like alphabetical the way that it's sorted?
Yeah, so when we add to the tree, we're going to do it in a way that maintains this binary search tree characteristic. So we'll talk about adding tomorrow, and then we'll start looking at some code.
Okay, so it's going to be sorted based off of,
License plate.
right, and that's not a numerical value. So ASCII characters?
Yep.
Or- okay.
Yeah, we use string compare.
Guess we could combine it with PA3 if instead of chaining, we set a binary tree off of.
Yeah, could do that.
That's right.
All right, I will see you tomorrow.